Hey everyone, welcome back to another episode of Engineering Roundtable. This week we're going to be talking about audio spectrum analysis and how to analyze the audio spectrum using a microcontroller, the methods of spectrum analysis, and what to do once you have analyzed an audio spectrum. We're going to talk about the methods of filtering, what a spectrum analyzer is, and then we're going to analyze an audio signal, pull some data from it, and then do something pretty cool. I was looking back at recent videos and they have seemed a bit academic thus far. So this time I decided to do something a little more dangerous and fun. So stick around. So when we take a look at an audio signal on an oscilloscope, it looks like this. It's this big, nasty, noisy looking signal. And that's because all the frequencies of the music or whatever sound you're trying to play are included in this signal. Now, that's not very good. If we just feed that into a microcontroller, say on an analog line and on an Arduino, all you're going to get is the voltage level of the overall signal. Unless it's just a bass drum or a very simple audio signal, you're not going to be able to pull out different frequencies, be able to tell when different things are happening in the music. All you're going to see is the voltage level of the signal. What we want to do is called spectrum analysis. We want to break this signal down into its different parts. So we want a voltage level or an input for the bass drum, for the low frequencies, the bass and the drums, and then a high frequency for the snare, mid frequency for the guitars, things like that. So we can make something react to it. So the way that we do this is called signal processing. There are a lot of ways to do signal processing. Pete talked about one of them in his last video, which was filtering. We can actually build hardware filters out of op amps and resistors and capacitors to pull a single band or a high band or a low band out of the audio signal that we want and allow that to just be passed through the filter. Take all the other bands out. A second way to do it is with specialized hardware. There are chips called DSP chips, digital signal processing chips, that have a specialized architecture to pull in a signal, whether it be noisy audio or data or something. These DSP chips have a specialized architecture that allows them to quickly and efficiently operate on a signal, whether it be a noisy audio signal or a signal with some data running through it. The architecture allows the hardware to pull in a buffer of data, sample it, and operate in that sample in real time. So the signal comes in and the data or whatever you're trying to pull out is pulled out quickly. The third method of digital signal processing, the third common method, is to take a normal microcontroller and write in DSP algorithms. That is the method where the user has the most control. If I write my own DSP algorithm, I know exactly what's going on. I can change sampling rates, sampling sizes. So in the Arduino, for example, you are sampling a signal at a certain rate, as high a rate as you can get it without running out of bandwidth. And you are trying to take the largest samples you can without running out of memory, and running a mathematical operation, a discrete mathematical operation on that signal that you pulled in. So you've got this chunk of audio signal, you run this operation, and you try to pull data out of it, which is the way any DSP processor is essentially going to work, but the Arduino is only going to be running at 16 megahertz, and that's not quite fast enough to do a lot of heavy-duty DSP, which is why there's so much specialized hardware out there for that. There are cheaper chips that are built to do that kind of thing. It can be done on the Arduino, and there are some very good libraries written for doing things like a Fourier transform, these mathematical operations on an Arduino, but they're all written in assembly, so they can be pretty difficult to hack. So let's talk about how the audio signal is actually analyzed in most cases. We've got this signal that's nice and noisy. We don't know what the power at any certain frequency is, and we need a mathematical operation to run on this. Something to do to take the individual bands and quantize them. The operation we want to run on this signal is called a fast Fourier transform. A fast Fourier transform is a specialized kind of a Fourier transform, which is a continuous mathematical operation to break a signal down into its individual frequencies. I can take this signal, run a Fourier transform, and find the signal power at any point in time at any frequency. I would specify a frequency, run the operation, and then I would come up with a value for that particular frequency. This messy signal is actually made up of an infinite number of high and low frequency parts. And I can break this down infinitely into what I want. When you're doing this in the real world, this has to be done discretely, because when you pull this signal into a controller or a device, you take samples as fast as you can and store those in a buffer. That becomes a series of just numbers. And the algorithm to run on that series of numbers is called the fast Fourier transform, which runs on discrete values. Once you run the Fourier transform on that buffer of values that you have, you end up with a power level at a certain frequency, a quantization of the power at whatever frequency you're trying to operate on. From 20 hertz to 1 kilohertz, you'll have this power level. From 1K to 10K, you'll have this power level. Now we're starting to pull out the frequency components of that audio signal. We could be using some hardware to pull out a certain band here, or we could use some specialized hardware to pull out all the bands. So say you want to trigger an LED, you want to turn an LED on and off. What you do is you set a threshold here that says every time, say, this frequency value goes above this threshold, turn on the LED. In this case, if you just had, say, a bass drum beat, it would, every time the drum hit, it would go over this threshold value, turn on an LED. Up to the point where you have the frequency band analyzed that you're trying to operate with, everything's relatively easy. There's a lot of specialized hardware libraries out there. The problem comes when you're analyzing an audio signal. So when a lot of people get into hobby electronics, one of the first things they want to do is make something sound reactive. And they don't realize that that can be pretty tricky. And the reason for that is an audio signal is relatively noisy. Most audio or popular songs you hear on the radio are compressed so heavily that a lot of the frequency information is compressed out of them. Even still, when using an uncompressed audio file, something recorded before 1980, for example, the sounds that you're hearing, for example, like a snare drum, is going to have multiple frequency components within it. So you hit the snare drum and maybe you get a very high frequency, but you'll also get a lot of mid frequencies as well. The snare drum is not a frequency in itself that you can pull out. And if you do want to pull out just the snare drum, you have to do some really high level analysis. The best you can do is try to pick out something that's pretty unique, like a bass drum, something that's constant and louder than everything else, and set a threshold that gets you pretty close. Even though the bass drum is going past this threshold, other instruments, when they come into the song, can have frequency components like the bass drum and then add up to beat that threshold. So without doing some very refined analysis, you're never going to get exactly what you want. It can be really tricky, and it varies from song to song, artist to artist, instrument to instrument. So what we're going to do today is just that. We're going to use an Arduino and a SparkFun Spectrum Shield to pull out this low frequency power and then have it operate on something. This is our rig. This is our project. Ignore this bit for now, and we're just going to talk about the electronics. What I've got here is an Arduino with a SparkFun Spectrum Shield on top of it, a battery pack, and then a MOSFET circuit that is controlling something over here that you're ignoring right now. The important part of this is the spectrum shield. What this does is it has two audio jacks, one for in and one for out, where I can plug in an audio device. And in this case, it's coming out of a little synthesizer I have here. It pulls in the audio signal from the synthesizer, and the chip on board takes that audio signal and spits out 7 frequency bands in real time. So on my Arduino, all I have to do is tell it what frequency band I'd like. It spits out an analog value. In this case, I'm analyzing the second to lowest frequency value that is coming out of the spectrum shield, and I just have to toggle a pin. It's really easy to use. So I toggle a pin, it updates its analog out, the Arduino reads an analog in. Based on how large or small that value is, I know whether or not to trigger the MOSFET circuit. So the spectrum shield is going to analyze the audio signal. The Arduino is going to check the threshold value for the second to lowest band, which after a bit of playing, I've found is the bass drum. It is then going to toggle the MOSFET circuit. The MOSFET circuit is going to target the solenoid on the mystery thing here, which is going to open it up. What is this mystery thing? This is a forge torch that I built for fun to play with fire. So our electronics are going to be triggering the solenoid that opens the fuel line and creates flame. The reason I'm in my garage instead of SparkFun is because this comes with a disclaimer. This forge torch, even though I'm going to show you how to build it, is dangerous. You should never ever try this or think about it ever, because you're going to hurt yourself. If you do think about it, I want you to think especially about the safety precautions that you're not going to need because you're not going to use this, namely a fire extinguisher, some sort of face protection, some nice heat-resistant gloves. Whenever you're working with fire, it's best to keep a wet towel around just in case. I think the most important thing other than this is if you think about doing this but don't do it, because you shouldn't, always have someone else around in case you don't catch on fire and they don't have to put you out. So let's talk about this torch that you're not going to build. This consists of a 30 psi regulator, which is connected to 24 volt solenoid, which opens and closes the fuel line. The solenoid is run by the MOSFET circuit connected to the Arduino. Some Schedule 80 piping that I've made into this nozzle. For my purposes, I just wanted a simple flame, and this is the simplest way I could find to make a big flame. The most difficult part of building this was fabricating the nozzle. So up here, I've got what is called a venturi, which is a fuel nozzle that also brings in air. In order to ignite propane, which is not self-oxidizing, you need a certain amount of airflow in order to get a good, clean flame. In order to create the kind of flame I want, I have to be able to control that air. This is 2 pieces of laser cut acrylic. I could have done this with steel, but it would have taken me longer. There are holes in the back of both of these pieces. I can twist this to open and close and control the airflow. What we've got here is essentially a miniature version of what you've got on your barbecue grill. A barbecue grill that runs on propane is going to have several smaller venturis that pull in air, mix it with propane, and then send it to the burners. So on the inside of this nozzle, here's where the gas is coming up from the solenoid. It takes a turn, and then it runs down 1/2 inch Schedule 80 steel pipe. At the end of that steel pipe is a welding tip. So this welding nozzle has a very small hole at the end of it that allows for a very high power jet of propane when this is turned on. Around the outside is the 1 1/4 inch larger part of the nozzle that has the acrylic air control at the back. So when this is turned on, the gas starts coming out of the smaller nozzle, and when this ignites, it begins to pull air in through the back of this, giving us a big flame at the end of this nozzle. Well, I hope you enjoyed that and learned a lot, and never try it at home. And be sure to tune in 2 weeks for another engineering roundtable with Joel.